Well, I hope you're still in the mood to go on a little further. We have, in the first part today, shown what we do to the structure on side forward, calculation-wise backward. As mentioned before, a little contra situation in this theoretical run is when we have auxiliary structures which are not present when the bridge is completed, because there we have to do a little additional thinking. A typical example is the situation, what I've shown here for the East Huntington Bridge in the US, where we have a tower, a slender tower, good enough for the final stage, and contrary to Mannheim Nord, we need to free cantilever to both sides. You remember Mannheim Nord, what we've seen there, the approach span was completely on land, and we had only free cantilevering here and immediately put in the tiebacks. Now if we have to free cantilever to both sides because the water is too deep and there is no piers in the end, very often ship traffic doesn't permit to put in auxiliary piers, or it's cheaper not to do it. So when we have that situation, we have the free cantilevering, and in this case lifting heavy precast elements left and right, and the moment the tower couldn't take. So what we do is we stay the tower with auxiliary cables to the hold down pier and here to the other pier, and we see it here. We have used the final anchorage and hung it into the tower, and we also see a comparatively big sag, much bigger sag than in the end, which has to do that we have full stress in this cable only when we have full stress in this cable only when we have the lifting heavy weight on a maximum lever arm on the other side. Then the slack is taken out of the cable. But when the heavy weight is on this side and the tower leans to me, then of course the cable is unloaded and we get a heavy sag. During construction, we very often have to take into account the change of sag, the change of E modulus of the tower into effective E modulus, change of sag because the stresses change much more than in the final stage. You remember 7th semester, I told you effective modulus of elasticity, stress to the power of 3. Now that comes in here, but that's a minor point. So our construction engineering, what do? We think and calculate first forward, that's all we have, in order to find out how, going backwards, we have to install with what force the auxiliary stays at the tower. The auxiliary stay forces at the end of construction are those which we introduce when calculating backwards. And so we must calculate first forward the cable forces in order to be able in the backwards calculation to know with what forces we have to introduce. How do we determine the auxiliary stay forces in the tower? Well, we install with a certain forward-backward zero force, which we determine in such way. Governing is here for the side span loading, the before closure here at the side span, so lifting the element with the biggest lever arm, say 300 tons, with the biggest lever arm, which means we have the biggest force in this backstay cable. So in there is the maximum force from lifting plus a minimum force for, say, post-tensioning at the beginning. And the other way around, the biggest force in this auxiliary tower cable, which is in the position of the final backstay cable, is when we lift the last element with the biggest lever arm to the other side. Then this is the biggest force in here. So by knowing the biggest force and permissible stresses, we can then calculate the required steel diameter of the cable, and we can choose a certain minimum initial force, and we have the diameter of the cable. And now in our backward calculation we can install the auxiliary backstay and tower stays with the force we have calculated from the condition of lifting left or right. So backwards we install it, have it in as long as we need it, and then once we don't need it, which is basically when we have taken out the last beam elements, we remove the auxiliary tower stays with the force which is then there, which should be the chosen force at installation S0. So that gives us auxiliary tower stays introduced. Now, as always in life, there is room for improvement. We did 2 cable stayed bridges in the US in this way, staying the tower forward backward. But sometime later in Argentina, it was done a little bit more. I just show this picture, and there we said, okay, what we do is we either have a balanced system, left and right, or if we have it unbalanced, it's always unbalanced to the main side, to the river side, which means we do not have the situation that we have unbalance here and need staying to here. And with that system we can do with one backstay only, because we have a certain minimum force in here which the tower must be able to take, but then it's either balanced, no additional force in the auxiliary stay, or it's balanced to the river. Okay, then it's getting a higher force. So we get rid of the 4-stay auxiliary stay, which is a good thing, because the 4-stay auxiliary can be reached by ships. And Murphy's law, one of Murphy's law for construction engineering is, if a ship can reach a cable, it will run into it. Remember, and it did indeed for this system also. We had a ship running into there, and the cable didn't snap, and there was quite some ado, but nothing happened. So since then I'd rather avoid a reachable cable, and this was one of the consequences here. And we see here the situation where we have a sturdy tower. We have here the beam just cantilevering or being eccentric to the main span, and we have only the one backstay which takes care of this unsymmetric situation. So only one backstay, and again the calculation is similar to what we had. Now we had auxiliary stays at the tower. I don't know, unfortunately or fortunately, we also have some similar considerations for the beam construction. There we also have various types of auxiliary stays and cables and tiebacks, which makes life in construction engineering so much more interesting. So the Houston Ship Channel crossing at Baytown is very close to the Gulf of Mexico. Every year we hear the tornadoes going through there. Catherine was one of the better ones there. And this bridge is right in the middle of the typical hurricane path. So, of course, during construction we had to assume the loading hurricane. I told you all sorts of things about aerodynamic stability. You may not be happy to remember, but I did. And there we discussed all that. Now, here it would not have been possible by free cantilevering to both sides to be safe against a hurricane when it really hits during construction, the bridge. It's clear, a bridge is much more vulnerable against high winds in the cantilever stage when it's not connected than in the final stage. We've done certain things in the final stage, but there the problem wasn't so critical. And there have been several hurricanes going over the bridge during its lifetime. One, 1996, I think we opened it. Did well. And here, to be sure, we used auxiliary tie downs to, after we had a certain initial free cantilevering, tie downs to take care of the hurricane. And you see it's not symmetric. This goes directly to the tower piers. This has the same distance but has special anchorages there. And also, if we look onto it in the driver's view, we have transverse, we have vertical. So we have taken care of all three modes in which the beam may oscillate. And it worked well because we had hurricanes, more than one, going over. And without tie down, it wouldn't have worked. I think the figure was, Bob Scanlon, our dynamic expert, calculated plus minus 1.5 meters going up and down, and it was measured. It happened. But it was calculated, and we could take it well. Let me see. Is that true? Yeah. This was just an auxiliary consideration. We can, as one consideration to tie down the beam. We can also try to get rid of tie downs completely. You remember for free cantilevering we first had both sides, then we had one side only. Always because we took the full weight of a heavy concrete element, 300 tons, completely eccentric. Well, I mean, with a little thinking, you can say, why the hell do I need a full element eccentric? Can't I do with just half? So, of course, it can be done. We start here with a half and here with a 1, and then we add here and there, and then we always have only 1/2 element eccentric. So, we halve the moments about the tower, and life is much easier, and we may get away without auxiliary stays for the tower at all. You can also refine it. It's in the lecture, going stepwise and all sorts of things. Now, an example for stiff towers are the Zárate, Brasilago bridges in Argentina. We mentioned them before. First road and railway cable stayed bridges, 330 meters. Because of the railway, the towers had to be rather sturdy concrete towers by themselves. That's, of course, one important thing. If you have fiddly steel towers, they can't take much. If you have sturdy concrete towers from the beginning, you're in a much better position. And then we have a steel beam. Now steel beams have of course much lighter sections to lift, not 300 tons, but maybe, depends. Composite steel grid may have 60 tons, steel beam section may have 100 tons. So this combination of sturdy concrete towers and light element permit us no auxiliary stays or tie downs at all, and we are thankful for that because it makes construction engineering easier. Now, the travelers at the tip of the cantilever may need some additional help, or the beam needs help. And so the traveler with a weight may have to be tied back somehow. Also, there are various possibilities. The main problem is naturally that the weight which comes up here acts on the structure, as I showed you before, via the support reactions of the derrick. And this is an elastically supported beam, elastically supported by the stay cables. And the moment influence line, you may recall, is very steep here, goes back fast. But it's, in one word, such a beam is very, very sensitive against vertical loads at the tip. The same load 3 cables back doesn't do much. But here, we don't like it. So very often the beam would be overloaded by this negative moment, tension at the top, from the weight of the new element plus derrick at the tip. So we have 2 possibilities. Either we strengthen the beam, which is insofar not very effective as we have only the depth of the beam for an inner lever arm. 2 meters or something, maybe beam depth, modern. Or we tie back the derrick either to the tower, then suddenly we have 150 meter depth, or we go back here, which is in effect the same, and that's what we prefer to do. We do not normally, for this load situation, strengthen the beam, but find some way to relieve the load here. The simplest way is, instead of tying the derrick back short, tie it long, theoretically horizontally to the tower back, which was done, I'll show you in a moment, here. You see the tiebacks, the derrick, went practically horizontally to the tower, thereby strongly relieving the vertical component here. So the simplest way is to the derrick tie back. Instead of going to the first cable, we go to here. That means the force couple from this weight, and that means the moment here at the tip is reduced proportionally if we tie the derrick further back. One example, again, the Sarata bridges, where at least the derrick tieback went back 2 cable distances instead of going closely here. We can see it here. Another little bit more complicated was for the Pesco-Kennewick bridge. I mentioned that was when Leonhard sent me alone to the United States in 1976 to do the design for this bridge. Because there was no cable-stayed bridge in the US until then. Nobody knew, no contractor, no designer, no nobody, except poor little me. I had to think much of it of myself because I didn't know either. Then we also had to design, at least put on the drawings to show the contractor a way he could put the bridge together. I mean, he could choose something different. And of course he did. Whatever we put on the drawings, the contractor starts to say, no good, doesn't work. And then after 3 months he came back, well, maybe it's not so bad at all. Let's go this way. That's very, very typical. But with our bridges we have always put one optional construction method on the drawings and have said, for this construction method we have checked the beam system and additional quantities required for that are included. That's a big thing for a contractor. Now, if you, contractor, choose something different, up to you, but then you are responsible for additional quantities. And that makes him think twice always. So very often your system comes. And anyway, here we had the 300 ton, was very early, 1976 as I said. We had here the 300 ton precast element, you see it lift up. And then we said, okay, we used, at that time there was nothing in the US, we used a lift slab from buildings hydraulic system. And we had the horizontal backbone of the traveler here, which then was to hang back the traveler into the tower to unload the beam. The beam couldn't take it, precast joints couldn't take it. So this is a tie back. And in addition, we had to stay the tower because it was free cantilevering to both sides with auxiliary stays. So we have here, we see here this one is the forward tower, auxiliary tower stay, where the ships are due to run in. This is the auxiliary tieback of the traveler going up here. And then we have the final cables, and here this cable guide, what we used to call in South America banana, is for pulling up the cables and getting them installed here in the final position. So it's a little complicated, but it worked very well, amazing enough. And the play of forces, of course, is we assume that during lifting we pull so much at the auxiliary cable that it lifts off the front support and rests only here. I told you the influence line for a moment is very steep, and the beam likes it much better being loaded 1, 2, 3 cables back than at the front cable. And the play of forces, vertical forces, is like that. Just a little remark, not shown here, is an important horizontal component of this auxiliary cable. That's what we have to pay for. And it's not easy to take this heavy auxiliary horizontal component into the beam. It was done here with a big shear lag and post-tensioning. Not easy. Okay, this is lifting a traveler off the supports. Now we come to cast in place concrete beams. Until now I've shown for clarity precast elements. They are heavy, and you know you can understand it very easy. Now when we have a cast in place beam, then we cantilever from one permanent stay cable to the other. That may be something like 10 meters, roughly speaking. And then depending on the depths, if we have only 1 meter depth of a beam, and cantilever that 10 meters, that's 1 in 10 for a cantilever. And there we realize already, maybe too much for the beam. So what we can do then is we can support this formwork traveler with auxiliary tiebacks, auxiliary stay cables, which are anchored here, hung back to the tower. We can see it here that they are tied to the tip of the traveler and hung back. Now, they have two disadvantages. First of all, they have to be elongated for every new section. And it just is awkward and time-consuming, even if you have some screwed connections or so, to elongate these cables. They are heavy, it takes time. Secondly, because the first auxiliary stay cable remains in, it's just elongated, it has all the cables, all the pieces of the cables have to be sized for the biggest force, which of course occurs at the tip, at the end of free cantilevering. So for the most of their life, they are oversized. You need a lot of cable steel. And then the idea of reusing auxiliary ties, it's always put into discussion, it never works. Forget about it, you've got to scrap them. So then you know the cost, it's expensive. So we tried to get some ways around. And one, I'm just thinking, how does that? Ah, yeah. Moment. Okay, that was in the last one. We can, if we try to get rid of this auxiliary hanging back of the traveler, we have the chance, if then the beam here is lying on both supports, it's not lifted off as we have done here. Here we've lifted it off from the front support, then we leave it on, and then of course we have here the weight plus the moment from the eccentricity, which is an important force, and that can only work if I have a deep beam and or a small cable distance or element length. I mentioned to you as one extreme 10 meter cable distance, 1 meter beam depth, 1 in 10 for a cantilever probably doesn't work. Completely different situation for the Cap Shui Mun Bridge in Hong Kong, going to the new, well, formerly new Lantau Airport. And that, I've mentioned that several times to you before, is a double deck cross section. We have 6 lanes of highway on top, and we have a rapid transit railway plus emergency lanes on the bottom. So we have a depth of something like 8 meters. On the other hand, we have rather close cable spacing of something like 6 meters. So we have 6 meter cantilevering for 8 meter depths. Well, there we know without very little additional, we can lift the full weight with this lifting beam supported 2 cables back. And that was done. We see it here. It's one of the heaviest elements ever lifted. I mentioned it before because it's composite. It has concrete top and bottom slabs and steel in between. And it was installed with the concrete slabs on. So we had a weight of something like 500 tons, which makes it rather heavy. But no additional supports were needed because we had, for some 6 meter long elements, some 8 meter beam depths, and we could take it like this. Now, to sum it up, we have discussed today the, let me put it, so second half of cable-stayed bridge design. The first half is the final stage, where we are free to choose a system and all sorts of things. And the second half is, how do we put in the first part, chosen system together? How do we construct the bridge? Last time I gave you an overview over the possibilities, how we can do it with free cantilevering and launching and all sorts of things. And today I tried to familiarize you with the way how to check stresses during construction for a chosen construction method, and how to tell the site what to check in order to be sure to arrive where we want to. At the final stage, after shrinkage and creep, we cannot do these calculations by hand because here it has to be precise and we have a highly statically indeterminate system. So we use a computer, and I've shown you what commands you have to give the computer to apply loads, to open joints, to be able to take out elements, and in this way to dismantle the bridge. And we know at the very end all action forces must be zero. If some is still fiddling around in the air without a member, something is wrong. It's a very simple and a very helpful criterion. We have the easiest way by using a floating crane which just takes off loads of the bridge but doesn't put any temporary on. But life is not so easy all the time, so very often we have to use a derrick which we have to place and move and take off. We may have to use auxiliary temporary stays for, e.g., staying the towers because of eccentric beam sections with large cantilevers. And because they are not present at the end, we do not know, backward thinking, with which force we install them. So we have first calculate forward to find the force and then backwards. In order not to overload the beam tip during lifting of elements, we may have to use some auxiliary tiebacks to relieve the beam tip of the weight of the being lifted element. For the construction engineering, this only means the loads we have to put onto the beam are reduced. That's all the beam knows of that. He has less high loads. And we mentioned, depending on the span to depth ratio of the cantilever, we can sometimes, if we have a very deep beam with small cantilever lengths, we may be able to lift very heavy elements without any auxiliary tiebacks. Thank you very much.